Hi, welcome back. So in the last video we have talked about how fission gas swelling is important, and of course we were left at trying to figure out the force balance that's acting on the bubble in equilibrium. So what's the force acting on the bubble during equilibrium process? So there's a pressure. So for a bubble in a solid, there are forces acting by the solid on the bubble, and the bubble will have some kind of pressure that's acting on the surrounding solid. So at equilibrium, I will put it this way: forces in, so forces into the bubble equals to force out. Otherwise, there will be a change in the bubble size. As per Newton's second law. In other words, the pressure on outside by the bubble equals to the internal bubble pressure. Pressure by outside, that means the solid on the bubble, equals the pressure by the bubble on the outside. That means the pressure by this bubble on the fuel matrix. So in a bubble there will be, so on this bubble the forces that are compressing the bubble, compressing or pushing forces, there will be a surface tension stress, and that will be plus an external stress. And what is this external stress? Let's say the fuel pellet is being compressed, maybe this way, and then if it's compressed this way, okay, it's compressed this way externally, so there will be some external stress that is being experienced by this solid, and that will of course impact the forces that are acting on this bubble. So that's what's called external stress. But of course in the fuel pellet, the external stresses that are acting on this fuel pellet may not be so much as compared to let's say the forces that are acting within the bubble itself. So this assumption where we neglect the external stress, we call it a stress-free solid. When we hear the term stress-free solid, it just means that the external stress equals to 0 or neglected, or is neglected. So this is balanced by the push-out forces. Okay, the bubble is trying to push out, so to speak. So we will have the internal bubble pressure. So P over rho equals to KT. So this is the bubble pressure that we are talking about. Okay. So let's take a look at the surface tension stress. How do we quantify surface tension? We use this term called gamma, and that is surface tension. This is surface tension, and this is force per unit length. Okay. Now we don't have to kind of measure the force of the entire bubble. We just need to find the representative force per unit area. Okay. So if we have a bubble, okay, and the surface, and let's just consider this part. Let's consider here. Okay, surface tension will be acting in this direction. Okay, surface tension will be pulling sort of in this direction. It's tangential to the surface it's acting on. Okay, so if you were to zoom into this part, okay, so let's say this is a small chunk of that sphere. The radius r is here, and then we'll draw a straight line from this to this. So this is an isosceles kind of a system. Okay, we have this length here. From here to here, we will call this small r. Why? If you imagine in a 3D, if we take a cone out of this sphere, out of this bubble, this will be a circle kind of thing here, and this is like a convex piece of lens or something like that. It looks like a lens, it's just a convex piece of bubble, so to speak. Okay, so the surface tension again is tangential in this way. This is the force per unit length. So F over M, M being the meters, or let's put it this way, gamma equals to force per unit length. So if we want to look at the force per unit area, that's pushing down into the bubble, force per area, pushing into the bubble, we will need gamma times some sort of length, the representative length, over some representative area. So if you just to consider this small little part, and we assume that this is repeated throughout the bubble, this is the same no matter which chunk, which slice of the cone you take. Okay, so we can do this as follows. The area, the normal area anyway, that is pi r square, that is the small r. This is not the radius of the sphere, but it's this radius of this small little circular chunk. Okay, and the length here is this is the circumference of this flat circle. Okay, circumference of this flat circle, so that's 2 pi r. And gamma over here, this is the resolved gamma. Okay, this should be the vertical component of gamma. So gamma is the surface tension is acting this way, but we just want to look at the forces acting down this way. Okay, so it's going directly down into the bubble. Anything else will be resolved tangentially. So there's a vertical component and then there's a horizontal component. We are only interested in the vertical component. So how can we find this vertical component? Well, we will have to use trigonometry again. Alright, so what we can do is this. We'll define a theta by such. Let's say this is some angle theta. So, okay, this is some angle theta. And so that sine theta equals to the opposite over the hypotenuse. So sine theta equals to small r over big R. So let's just write that down first. Small r over big R. Okay. So we want to find this component that's pointing downwards. Now, how do we find the component pointing downwards? So we need to find this component. Okay, you need to find this component, and this is gamma. So this is theta, and this is so-called tangential. Tangential meaning it's 90 degrees. Tangential means it's 90 degrees. So that this will be the angle theta over here. Okay, tangential means the gamma is at 90 degrees at this point, and this is the radius, so gamma is perpendicular to the radius, orthogonal to the radius. So this is theta over here, and the vertical component pointing down will be gamma sine theta. Gamma sine theta. So let's put this into our force per unit area expression. So we have a length, which is 2 pi r, times the vertical component, gamma sine theta, over pi r square. And gamma sine theta is simply small r over big R, and this will be pi r square. You can see immediately that the pi will cancel out and the small r will cancel out. And what we are left with is 2 gamma over r. This is the surface tension force, or surface tension stress. Okay, so we have found out one component already. Okay, that is this one. So P equals to 2 gamma over R plus sigma external. But again, for simplicity's sake, we are just going to ignore this, and we assume a stress-free solid, which is quite applicable for our fuel. Stress-free solid assumption. Okay, so P equals to 2 gamma over R. Okay, so what are some typical values? What are some typical values of this pressure? So gamma for uranium oxide, that has been so-called measured around 1 Newton per meter, and R equals on the order of 10 nanometers. This is from electron microscopy. Okay, this one is from yeah, you have to see Professor Olander's book, chapter 13, to see how this is measured. Okay, but we have a pressure on the order of 2 times 1 over 10 times 10 to the minus 9 meter. Let's see how many pascals that is. Okay, I'm just going to pull Excel out now. Okay, so what we have is about 20. Okay, let's use scientific. Okay, 2 times 10 to the 8 Pascal, or 20 megapascal. Or rather, it's 200 megapascal. 200 megapascal. And 200 megapascal is a pretty big, large amount of pressure. So even if we had some stresses, forces acting on the fuel pellet, it's still pretty small compared to this. And that's why we can sort of think of it as a stress-free solid. Okay. Anyway, the fuel is not meant to bear weight, so that's the other reason that we can assume it's a stress-free solid. So this is some typical value of what the pressure can be like inside that bubble. So the other thing about this equation, you can see P equals to 2 gamma over R. The pressure changes as with 1 over R. So with a smaller bubble, the surface tension pressure that's holding the gas in is higher. So the bubbles actually become denser when they're smaller. And what does this mean? Smaller bubbles means less swelling for same amount of gas. Why? Because with higher pressure, the atoms are squished closer together, so their density increases. Okay? Anyway, so let's substitute what we have back into the van der Waals equation. So P equals to P 1 over rho G minus B equals to KT. So what do we have? P equals to 2 gamma over R. And what is rho G? Rho G equals to what was the expression before? Yep. We have something like this before in the last video. M over 4 third pi of Q. So we have M over 4 over 3 pi R cubed. And R is the bubble radius. And M is the number density, or atoms, or number of atoms per gas bubble. Okay, so let's just substitute that in. Two gamma over R equals to times okay, we have this expression. All right. Or rather, let's make it let's get it a little more organized. We want to get this M as our subject. Okay, so let's switch things around a bit. So we have a KTR over 2 gamma. Bring this B to the other side. Okay, so we can find the M immediately. So let's find M. So we bring all this down here. Okay, so this is a stress-free solid. Stress-free solid assumption. So of course, if we were to consider ideal gas kind of assumption. Then this is a van der Waal. Here, ideal gas assumption B equals to 0, so we'll have this expression. Yep. Ideal gas is here, so we will cancel these R's out. The 2 will go on top, so 4/3 pi R square 2 gamma over kT. Okay, so we will have something like a 8 pi R square over 3 kT. So we will have something like that. And there's a gamma here as well. So it's 8 pi R square over 3 kT. That is what M will be like. And this is an expression for the number of atoms in a bubble for a given temperature, the surface tension, and everything else. Of course, the size of the bubble is to be taken into account. Anyway, let's substitute the values we previously discussed for the van der Waal case and the ideal gas case. And of course, we want to see how much the effect is. So remembering that B equals to 85 angstrom cube, okay, R equals to 110 times 10 to the minus 8 meter. T equals to, T equals to 1273 Kelvin. That's at 1000 degrees C. K equals 1.38 times 10 to the minus 23 in the SI units. Just can't remember off my head. So if this is substituted into Excel, we'll find that atoms will bubble. M equals to 0.42 times 10 to the 4 atoms per bubble. Whereas for the ideal gas case, where the calculations of course is a lot simpler, so I put VDW here for van der Waal. M ideal gas is equals to 4.7 times 10 to the 4 atom per bubble. So you can see for the ideal gas case and the van der Waal case is a very stark contrast. But usually ideal gas is very easy to calculate. But just take note that there's about a 50% discrepancy, and this will be quite important to take into account. Now, after all that, how do you find the swelling? So again, we have to find the delta V over V of the fission gas. Okay, and that's, how would that be equal to? This is the volume of the bubble, volume per bubble, times the number density of the bubble, which is times volume or number of bubble over total volume. So these two will just give you the number density of the bubble. So that's number of bubble per volume. Okay. Now, what do we need to do? Next thing we need to do is to substitute this R in with whatever expression we have here. Now, if you look at this equation, R appears in two places. So wanting to factor that out will not be so easy. So That's why sometimes ideal gas is sometimes used for easier calculation. Just that know that there's some discrepancy involved as shown earlier. So we'll use the ideal gas kind of assumption. So m equals 4 over 3 pi r square 2 gamma over kt, which is also equal to 8 over 3 8 pi r square gamma over 3 kt. Okay, so that is what we have. So now we need to make r the subject. So I'm going to shift some terms over. Okay, shift some terms over. So 3 kt goes on top. And I'm going to put 8 pi gamma at the bottom, and that will be equal to r square. So 3 ktm on top, 8 pi gamma at the bottom, and that will be equal to r square. But I can just do the square root of the whole thing to get r. Okay. And if we were to substitute our earlier equation from our mass balance, we'll know that this fact. Okay, so we can substitute the m into here to account for the fission rate. So m equals to y xe over the bubble number density. So in effect, r equals the square root of 3 kt over 8 pi gamma. So m will have yxe, f and t on top. So 5xe, f and t on top, and bubble number density at the bottom. So now that enables us to find the radius. So if we were to substitute all this in, we can find the swelling fraction as a function of whatever we have here. Okay, so that is our next step. Just draw this here. So again, from the last part, we find that this 3 kt over 8 pi gamma yxe f into t times the bubble number density. Okay. So next will be, you want to substitute that into the swelling formula. So that's equals to bubble number density to 4 over 3 pi r cubed. So whatever we have here, this is actually to the half power. So if we want to substitute into this r cubed equation, it's quite simple. mb 4 over 3 pi, whatever here is times 3 over 2. 3 kt over 8 pi gamma yxe ft over mb to the power of 3 over 2. Excuse me. So that's pretty much what we have here. Now if you want to do a substitution of a burn-up, you can do it as follows. If you want to use burn-up, because burn-up is very common, so ft over nu, we discussed this before, and this is number of u atoms per volume. So in effect, f dot t equals to burn up times number of uranium atoms. And just to be clear, this is inclusive of the uranium-238, not just the fissile uranium-235. Okay, so we substitute this in here. Okay, Ft will be replacing that. Okay, so this is the expression we have here. And then if we were to rewrite this in a very neat, concise form, we can also write it this way. So if we were to cancel all the pi's and all these numbers out, we will have this left. And we have a kt over 2 gamma and u yxe to the power of 3 over 2 times burn up 3 over 2 over root of the bubble number density, because this is at the bottom and that cancels with this, so you'll have a square root of and be at the bottom. Now this is our expression for swelling due to fission gas, mainly xenon, assuming the ideal gas and stress-free solid. We can see that our expression still requires knowledge of the bubble density, and the rest, all these have been discussed before. Now while we may not exactly know what the bubble density is, we can still plot swelling as a function of burn-up, as we kind of would want, so that we can find some upper limit, except that we can plot a family of curves for different bubble density. So if we were to substitute some representative numbers, okay, so if we were to substitute yxe equals to 0.25, so this represents all where xenon is not just xenon itself, it's xenon plus krypton, okay? So this represents all the heavy fission gases excluding helium, gamma being about 1 Newton per meter at the temperature of T equals to 1000 degrees C plus 273 K, K equals to 1.38 times 10 to the minus 23. And for the number of uranium atoms, so that is the mass over, this is the number of uranium atoms per cm cube, so we can take the density, 10.97 gram per cm cube, that's from Wikipedia or wherever you can find, over the molar mass, okay, 270, that's about 238 plus 16 plus 16. So that's 238 plus 32, that'll give you roughly 270. Of course, if you want to consider the isotopes and all that, yeah, sure, why not? But that will give you roughly this answer. Then you times Avogadro's constant, and that will give you the number of atoms per cm cube. And how much will the burn-up be? Depending on the enrichment, it will go from 0 to 5%. 5% is for 5% enriched uranium. So usually that kind of forms our upper limit if we don't consider breeding. Well, of course, if we do breed, we have to note that some of the uranium-238 will convert into plutonium-239, and the burn-up may be somewhat higher because there are more fissions. Remember, while the number of uranium atoms stays the same, there are more fissions that occur. So with breeding, the burn-up may be slightly higher than, let's say, the enrichment level. And enrichment is the, okay, enrichment is the number of fissile atoms as a function, compared to the number of total atoms. So it's the number of uranium-235 atoms as a percentage of the total uranium atoms there. So you can draw this graph. Yeah. draw a graph of, let's say, a volume swelling or radius. Can draw a radius graph first. Oh, never mind. Can just do a volume swelling. Delta V over V. And we have a burn-up fraction. Okay. Now, if we were to plot all this in Excel, we'll have a family of curves that look something like this. So, we will test for different bubble number densities. So we'll go from 10 to the 15 to 10 to the 19. So the typical median value is about 10 to the 17 bubble per cm cube if you look at Professor Olander's book. So we can plot from 10, 15, 10 to the 16, 10 to the 17, 10 to the 18, 10 to the 19, just to perform some parametric study. So we plot all this in Excel and plot a graph. And of course, if you actually want to plot it, you have to remember the unit conversions from cm cube to meter cube and all that kind of stuff. So it will look something like this. So the last one is 10 to the 19, 10 to the 18, 10 to the 17, 16 and 15. And this is less than 1%. So this is 0.01 of the swelling fraction. Here it can swell as much as 8% at the burn-up of about 0.05, since that is our kind of important point we want to consider, because that is about the enrichment level of the uranium. So regardless whether or not we know the bubble number density, we know that the the swelling is very dependent on bubble number density. Okay, and we generally don't want it more than 10 to the 17. We want it kind of the lesser the better. I mean, the more bubble density, the better. Okay, this should not be 10 to the 19. This should be 10 to the 15. So with more bubbles means there's a smaller size per bubble. So the density increases as was discussed before. Okay. So we may not get the bubble number density from, let's say, a pure mathematical derivation. We can still look at micrograms of fuel and get a guesstimate of bubble number density post-extraction from the reactor. And then we can refer back to these graphs to see how the fuel, or try and predict how it expands over time. And this is very useful for us to understand how much the fuel swells as a function of burn-up or time equivalently, depending on the characteristic bubble number density. Another neat thing is that after a long period of time, the bubble number density doesn't change as new implanted xenon atoms just join existing nucleation sites, causing the bubbles to grow. So NB will stay constant after a while. So that makes it useful because as soon as we get the samples from the reactor, that bubble number density is quite fixed for most of the lifetime of the fuel pellet. As it was discussed before, we looked at the graph. Okay, so it will kind of plateau after a while, and that's what makes the micrographs very useful, since they just do some the bubbles themselves just coalesce after a while. So thanks for watching. That's all I have for you now. I'll see you guys next time. Bye bye.